Welcome back to another hands-on session on unsupervised learning. In today's NIME's hands-on session, we'll be looking at PCA. PCA stands for Principal Component Analysis. This is one of the feature extraction technique used for reducing the dimensionality of the dataset while keeping the important features intact. So as usual, let's start with our CSV reader to pull in the data source. Let's configure the data source. Today we are having a data set of miles per gallon of several models of cars. And our target variable is miles per gallon based on different input features like cylinders, displacement, horsepower, weight, and acceleration, etc. So now that the data set is being read into the NIME, so let's get started with PCA. So even before we start with PCA, basically which deals with dimensionality reduction, we need to have a baseline model to see without PCA what is the variance, and then with PCA what does the variance looks like. So to demonstrate this, let us first build a vanilla linear regression model. As we know, because we are predicting a value here, miles per gallon, this is a typical regression problem. And to create a linear regression, we need to first do some kind of pre-processing in terms of the missing values, in terms of categorical variables like what we have the car name, which is a string. And then if you see uh, the statistics, there are some missing values. So let's read this two and then straight get into creating a linear regression. To deal with missing values, I am using the missing values node to filter out the string variable, which is the categorical variable. I'm using the column filter. I'm connecting both. For the missing values, I would want to treat the all the numerical values missing with mean. So I will apply this and see that, execute, and see that the missing values have been taken care. The horsepower, which was earlier 6, now showing 0 missing values. Now I will connect it to the column filter. Now, car name does not is a categorical variable because this is a linear regression. We want all the variables to be in the numerical format, and also the car name does not bring any value to the model building. So let's exclude this. Now we have our number of columns which are like 8. So let's, as any typical supervised learning, first we need to split the training data set into training and test. For that, I'm using the table partitioner. Because I'll be running a linear regression learner. I will use linear regression learner, and for predicting the model linear regression, I will use regression predictor. And to evaluate the performance of the model, I will use the numeric scorer. There's a detailed video on linear regression if you watch the 9 playlist series. For now, I'm connecting the table partitioner, and then by default, it takes the random sampling strategy, and this is how you execute. And then you get your first partition, second partition, which is the training and test data partition sets. I connect the partition, first partition, the training, to the linear regression model, configure my target variable, predicted variable, which is miles per gallon, and I have all the variables except the car name that are being used for the model building, model training, in fact. Now that the model has been trained, I want to evaluate, I want to predict based on this training. So I have connected it to the predictor, use the test data for prediction, and I will execute now. To evaluate the performance of this model, I will connect it to the Numeric Scorer. my reference variable and the actual value is the miles per gallon, and the predicted column is predicted mpg. So I will use both of them to evaluate the model results. So I get an r square of like 80% of r square is what I have achieved with a basic vanilla regression, linear regression. So now let's quickly see how do we do the same thing with PCA. How? By reducing these dimensions. Like when we the table partitioner had, in fact, had 8 columns. So now let us reduce this to three number of columns to three, and then see how the whole model gets built now. So to demonstrate that, let me keep this aside. To pull, I'll pull in the PCA node, connect the column filter to PCA, because as we said, the PCA is generally used as a pre-processing step. So even before doing the table partitioning, as part of the data pre-processing, I'm using the PCA. And the configuration for PCA is like, what are the dimensions, how many dimensions to be reduced to. So now the data set has got 8 columns. Now we want to reduce the dimensions to 3. And now because the MPG is our target variable, we will have to exclude that. We are using this all the features in the data set to create a new principal components which will reduce the dimensions of the features that we are being fed here. So let's apply and execute. I will also ask the model to remove the original data columns. So I see what are the new columns that get created after PCA. So if I look at the table now, now all the features that were initially there, the target variable remains as is. Now it has created 3 dimensions of the almost like 8 features that we have been fed to the model PCA node. It has created a 3 dimensions. Now using these 3 dimensions, we will do the logistic linear regression. Sorry. So because my linear regression workflow is already available here, I will just reuse this. I will connect now PCA because this was my pre-processing. I'm using PCA as part of pre-processing stage, connecting it to the partitioner node, and rest of everything remains same. I will execute all of them, all the nodes at one shot by selecting them. Now let me see what the numeric scorer looks like. Now R square is 0.68, which is almost like 70%. As we see here with PCA, that is with 3 dimensions that we have achieved with the PCA configuration, we are still able to achieve a reasonably fair R square, which is like almost 70%, unlike the standard linear regression, which is showing 80% of R square. This is fairly good given that we have used only 3 dimensions in our PCA model building. The R square prediction is 70%, unlike the standard model where we have 80%. This is reasonably good given that PCA has used only 3 dimensions. So to summarize, PCA is one of the dimensionality reduction technique in which we reduce the number of independent variables or features. By reducing the dimensionality, it helps to remove the multicollinearity, and also it reduces the storage requirements, computational times, makes the visualization better because now the number of independent variables are less, and it also avoids the curse of dimensionality, and hence because we are reducing the number of input features, it helps to reduce the overfitting. So hence henceforth dimensionality reduction and which is PCA plays a significant role in analyzing data as a pre-processing step. Thank you for watching. See you in the next video.